Okay, students, next topic we are going to discuss is capacitance of a parallel plate capacitor. We'll find out the capacitance of the parallel plate capacitor. Initially, we have found the capacitance of a spherical conductor, and it was 4 pi epsilon naught R. Now, we will find out the capacitance of parallel plate capacitor. Parallel plate capacitor is an arrangement of two parallel conducting plates of equal area separated by air medium or any other insulating medium such as paper, mica, glass, wood, ceramic, etc. So first we'll discuss the capacitance of parallel plate capacitor when the medium between the two plates is air. And then after discussing the different type of dielectrics and insulators, we'll discuss what would happen to the capacitance of the capacitor when these mediums are placed between the two plates of the capacitor. So let us start. We have two parallel plates here, and you can see here both of the parallel plates are equal in area. Both of them, they have equal area, and equal and opposite charges are given here. One is having positive charge, another is having negative charge. A is the area of both of the plates, and let us consider the distance between the two plates is small d. Electric field between the two plates that we have discussed in the last lecture. Electric field between the two plates is uniform, and it is sigma by epsilon naught. And you see its value is independent of the distance of point of observation, and its direction is also same. So we can say that the uniform electric field exists between the two plates of the capacitor. Now, as you see, in order to find out the capacitance, the general formula of the capacitance is charge per unit voltage. So voltage is what? So we need to find out the voltage between the two plates of the capacitor. So voltage between the two plates of the capacitor, here you see distance is there. Electric field we have already derived. So voltage, so we can apply the formula that electric field is potential gradient, or dV is equal to E dR, or V is equal to E into dr. Here is what? Dr is the distance between the two plates, that is d here. So potential between the two plates is electric field into the distance in which it exists. Electric field is what? Electric field is sigma by epsilon naught, that we have already derived in the last lecture, into T. So this is what? This is the electric potential between the two plates of the capacitor. Or V is equal to, so sigma is what? Sigma is charge per unit area. So this is actually sigma. Sigma is charge per unit area into D over epsilon naught. But capacitance is what? That is charge per unit potential we have calculated here. So we'll substitute this value here, and you will get the expression of the capacitance. So when you will substitute V here, V is what? That is Q D over A epsilon naught. So Q will get cancelled, and you will get A epsilon naught over D. So this is the capacitance of parallel plate when there is no medium between the plates, or air is the medium between the two plates. So, and you can see here, this capacitance does not depend upon the potential. It does not depend upon how much charge is given to the plates. It does not depend upon the electric field or any other physical quantity. You can see here it depends upon area of the plates, it depends upon the distance between the two plates, and it depends upon which medium is placed between the two plates of the capacitor. So for any combination of the two plates, and when they are placed at certain distance, the capacitance will remain constant whatever the amount of the charge is given to both of the plates. So it depends upon the dimensions of the two plates, and it depends upon the medium between the two plates. So if the space between the plates is filled with dielectric medium of relative permittivity ER, then or some other medium is there between the two plates whose permittivity is epsilon, then we know that epsilon is replaced with epsilon naught epsilon R. So capacitance of a parallel plate capacitor is directly proportional to the area of the two plates. More is the area of the plate, more would be the capacity of the parallel plate capacitor. And second, it is inversely proportional to the distance of separation between the two plates. So D, it is inversely proportional to small d. Small d is the distance between the two plates. So if the two plates are lying closer to each other, then capacitance would be more. And if the distance between the two plates is more, capacitance would be less. Now the next topic is series combination of the capacitors. We already know the series combination of the resistors. When two resistors or three resistors, they are combined in series or in parallel, then the net resistance is affected. So similarly, we can combine the capacitances in series or in parallels, and we can find out the net capacity of the combination. So first combination we are going to discuss, that is the series combination. So here we are going to combine the capacitors in series. So C1 is one capacitor, C2 is another capacitor, C3 is another capacitor, third capacitor. So three capacitors we are going to consider here, and all the three are considered in series. Now let us consider, for giving them charge, we have used the battery whose potential is V here. And you see from here charge Q will travel, it will get positive charge, equal charge will develop here because this charge negative is coming from here only. So same positive and same negative will appear here, and using the same concept, same positive, same negative will appear here. So in all the three capacitors, same charge would develop when they are combined in series. So charge on the three capacitors would be same, but the potential drop across each capacitor would be different as per the capacity of the capacitor. So in series combination, charge is same in each capacitor. Potential is distributed in inverse proportion to the capacitances. Inverse proportion, why? Because we know that C is equal to Q over V. So more is the capacitance, less would be the potential. So here charge on each capacitance is same, but the potential is different. But we know that the net potential drop V1 plus V2 plus V3 is equal to V. But V is what? We need to write this potential in terms of the capacitance. So V is what? Q over C. V1 is what? Q over C1. V2 is Q over C2. V3 is Q over C3. So substituting these values of V, V1, V2 and V3 in this equation, you will get V as Q over C, Q over C1 plus Q over C2 plus Q over C3. Q is going to get cancelled. C is the equivalent capacitance or the effective capacitance, net capacitance. So here C is what? C, we have considered all the three capacitors as a, these three capacitors are considered as a single capacitor whose capacitance is C. So this is the equivalent capacitance C. So we can get 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So this is the equivalent capacitance. So what we can conclude from here, that when the capacitors are connected in series, then reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of all the capacitance. The effective capacitance in series combination is less than the least of all the individual capacitances. So this is one very important note, that the effective capacitance in series combination is always less than the least of all the capacitances. Suppose if you are having 1 microfarad, 3 microfarad, 5 microfarad capacitors, and they are connected in series, then effective value of the capacitance would be less than the least value, and least value here is 1 microfarad, means the effective or net capacitance would be less than 1 microfarad. So this was the series combination. Similarly, we can discuss the parallel combination of the capacitors. So let us again consider 3 capacitors C1, C2 and C3. They are connected in parallel. Let us consider they are being charged by the battery having potential V. And now we know that in parallel combination the potential across each capacitor would remain constant, but the charge would be different on each capacitor. Potential is same, charge is distributed in direct proportion to the capacitances. C is equal to Q over V. So as direct proportion to the capacitances, the charge would be distributed. So potential is same, charges are Q1, Q2, Q3, and but the total charge. So again, if you see, the battery is giving the charge Q to this combination. So Q would be equal to Q1 plus Q2 plus Q3, because the charge given by the battery is going to get distributed on these 3 capacitors. So Q is equal to Q1 plus Q2 plus Q3. But Q1 is what? C1 into V. So we are using the same formula of the capacitance. Capacitance is charge per unit voltage. So Q1 is C1 into V, Q2 is C2 into V, Q3 is 3 into V, and Q is C into V. C is what? C is the total or net capacitance of the combination. So net means all these this parallel combination of the capacitances is considered as a single capacitance, whose capacitance is C. So substituting the values of Q1, Q2, Q3 and Q in the first equation, and you will get the equivalent capacitance of the parallel combination of the capacitors. So here in this case, the net capacitance is the sum of the individual capacitances. So simply the all capacitances will get added when they are connected in parallel. The effective capacitance is the sum of the individual capacitances, and very important note here is the effective capacitance in parallel combination is larger than the largest of all the individual capacitances. So here also, if we are going to consider the same example, 1 microfarad, 3 microfarad, 5 microfarad, net capacitance would be, simply you need to add them, that is 8 microfarad, and here the net capacitance is greater than the largest value of the combination, that is 5 microfarad. So net capacitance would be 8 microfarad, which is greater than the largest value of the combination, that is 5 microfarad. So here this is the parallel combination of the capacitors. So what we can conclude, when the capacitors are connected in series, then reciprocal of the net capacitance is sum of the reciprocals of all capacitances. And when the capacitors are connected in parallel, net capacitance is sum of all the capacitances. So for this is sufficient. Energy losses we can discuss in the next lecture. So thank you.